8.4 Lesson 2, Trigonometric Substitution. Our objective for today is 1. You will be able to use trigonometric substitution to solve an integral. And we're going to look at 2 examples today. As we learned during Lesson 1, trigonometric substitution is useful for problems where the integrand contains a radical expression, and depending on what form the radical expression has, we may use one of these 3 trig substitutions, and when the trigonometric substitution is applied, it will result in the elimination of the radical expression. So for number 10, we have to look at the radical expression and decide which of these 3 forms it matches. So in the first form, you have the square root of the square of a constant minus the square of a variable expression. And in the third form, you have the square root of the square of a variable expression minus the square of a constant. And that's what we have for number 10. So we're going to use the third trig substitution for number 10, and we will take a look at how we do that for our first example, number 10. And when you look at number 14, again, to know which of these 3 trig substitutions you should use, you're going to look at the radical expression, which is the square root of 1 plus x squared. And of the 3 forms that you have here in the trigonometric substitution table, only one of them matches the radical expression from number 14. Here we have the square root of the square of a constant plus the square of a variable expression. For number 14, we're going to use the trigonometric substitution that is stated as number 2 from our table. So now we will begin by looking at number 10. As we saw in our lesson yesterday, the main steps are to begin with choosing the correct trig substitution to apply, using the trigonometric substitution to change variables, eliminating the radical expression, finding an antiderivative, and then going back to the original variable of integration by referring once again to our trig substitution, aided by the sketch of a right triangle. So as we discussed in the introduction to our lesson, we look at the form of the radical expression, and for number 10, it matches what we have here. We have the square root of the square of a variable expression minus the square of a constant. And for our problem, the variable expression is x. So we have u is equal to x, and the constant that is being squared would be 2, because 2 squared will give us 4. So we have x squared minus 2 squared. So u is equal to x, and a is equal to 2. So now we will go ahead and use the trig substitution. Let u, which in our case is x, be equal to a times secant theta. A is 2, and once you can figure that out, it becomes easier from here. The next step is to find the differential of x. So we have 2 times the derivative of secant, which is secant tangent, times the differential d theta. With this, we can now move on to our next step in the process, which is to change variables from x to theta by using our trigonometric substitution. So we want to have nothing in terms of x and everything in terms of theta. So you can do this as follows. You can replace the x in the denominator with 2 times secant theta. So we will have in the denominator 2 times secant theta. And then we will replace dx with 2 times secant theta times tangent theta d theta. Now we still have to deal with the radical expression that's in the numerator. So now we're going to have the square root of x squared. Now, of course, x is 2 times secant theta. So when we square that, we have 2 squared is 4, and then we have secant squared theta, and then we have minus 4. So now we have accomplished the change of variables step. The next thing that we need to do is simplify this as much as we can, and then use a trigonometric identity, a Pythagorean identity, and that would allow us to rewrite what we have in the radicand, and we will basically have the square root of a square quantity, and we'll be able to eliminate the radical sign. We will in fact be using the Pythagorean identity 1 plus tangent squared x is equal to secant squared x. And of course you can manipulate that by subtracting 1 from each side. And then that would give you tangent squared x is equal to secant squared x minus 1. So that's what we will be using here to help us eliminate the radical expression. Before we look at that, one thing that you can do very easily is to cancel the common factor of 2 that's in the denominator and the numerator, and cancel the common factor of secant theta that's in the denominator and the numerator. So now we will have in the radicand, we have 4 secant squared theta minus 4. The two terms have a common factor of 4, so I can factor that out, and I will have secant squared theta minus 1. And then I have tangent theta d theta. And I have the square root of a product, so I can write that as a product of the square roots. And I will replace secant squared theta minus 1 with tangent squared theta. The square root of 4 is 2, and I can factor that out of the integrand. And then I have the square root of tangent squared, which will be tangent theta, multiplied by the other factor of tangent theta, which will give me tangent squared theta for my integrand. What have we done? We took a problem, number 10, and we used this trigonometric substitution, changed variables, and simplified to get a problem that looks like something that we dealt with in the previous section with trigonometric integrals. So we're going to remember what we learned in section 8.3 to help us continue from here on out. Some things that will help us are knowing some basic differentiation rules and their corresponding integration rules. For example, we know that the derivative with respect to x of tangent x is secant squared x. So if we have the indefinite integral of secant squared x dx, the antiderivative will be tangent x plus c. And why do I bring this to your attention? After all, our integrand is not secant squared, it's tangent squared. If it were secant squared, we could use this, but we can rewrite our integrand using this Pythagorean identity as secant squared theta minus 1. And that's what we're going to do. Tangent squared theta will become secant squared theta minus 1. And the reason why we want to do that is because we know how to find an antiderivative of the indefinite integral of secant squared x dx, or secant squared theta d theta. And of course, it's very easy to find an antiderivative of the constant 1 with respect to theta. With that, I'm able to integrate and write 2 times the antiderivative of secant squared theta with respect to theta would be tangent theta, and the antiderivative of 1 with respect to theta is just theta. And then you have plus c. So we have found an antiderivative, but it is in terms of theta. Our original variable of integration is x. So now we must go back to x by referring back to our trigonometric substitution. So to go back to x, we will refer to our trigonometric substitution. X is equal to 2 times secant theta. We can divide both sides of the equation by 2 and get secant theta is equal to x over 2. And we can draw a right triangle with acute angle theta. And remembering the right triangle definitions of the trig functions sine, cosine, and tangent, and we can use our mnemonic device to help us remember that. So katoa, we know that secant is the reciprocal of cosine. So secant of theta is going to be hypotenuse over adjacent. So knowing that, we can label our triangle as follows. From the perspective of the angle theta, the acute angle theta, this would be the adjacent side, and of course the side opposite the right angle is the hypotenuse. So we have hypotenuse over adjacent. And then we're going to go ahead and find the length of the missing leg. So we're going to have a squared plus b squared is equal to c squared. So we have a squared plus 4 is equal to x squared, and we have a squared is equal to x squared minus 4. So we have a is equal to the square root of x squared minus 4. With that, I'm able to go back to my original variable of integration, which is x. So using my triangle, I know that tangent of theta is the ratio of the length of the opposite side to the length of the adjacent side. So tangent of theta would be opposite over adjacent. It would be the square root of x squared minus 4 over 2. And then theta can be found, and there are different possible expressions for theta in terms of x. This is not unique, but it is most straightforward to go ahead and use your trigonometric substitution. So you have secant theta is equal to x over 2. You can take the arc secant of both sides of this equation, and you can get theta is equal to the arc secant of x over 2. And again, as I said, this is not a unique way of going back to x for this particular term from our antiderivative, but it is the most straightforward way of going back, just starting with our trig substitution and taking arc secant. So we have minus arc secant of x over 2. And for that reason, you could have different forms of the answer. And then you have plus c. Although not required, you could distribute the 2 to each of the 2 terms. And if you decide to do that, then your antiderivative in terms of x would be in this form. Our next example is number 14, and we have the indefinite integral of 9x cubed over the square root of 1 plus x squared dx. The first step is to decide which of the 3 trig substitutions you will use. And the reason why you might think of using a trig substitution is because there is a radical expression in the integrand, and we know that a trig substitution could be useful for us to eliminate the radical expression. So we see that we have the square root of 1 plus x squared in the denominator of the integrand. And of these three radical expressions that we have in our table for trigonometric substitution, only one of them has a sum in the radicand. And what we have for number 14 matches that. We have for the radicand the sum of the square of a constant plus the square of a variable expression. So we're going to have a is equal to 1, and we're going to have u is equal to x. So our trigonometric substitution is let u be equal to a times tangent theta. For us, u is x, so we will have x is equal to a, which is 1 for us, 1 times tangent theta. So once you have that figured out, you're just going to find the differential of x. The derivative of tangent is secant squared theta. And what else do we have here? What we have here is going to the next step, which is to change variables using our trigonometric substitution. So after we're done changing variables, nothing should be in terms of x and everything should be in terms of theta. So we can begin by looking at dx. We will replace dx with secant squared theta d theta. And then in the numerator we have 9x cubed. We know x is tangent theta, so x cubed would be tangent cubed theta. And in the denominator we have our radical expression, the square root of 1 plus x squared. And of course x squared would be tangent squared theta because x is tangent theta. So you can see that we've done our change of variables step. The next thing that we'd like to do is use a Pythagorean identity to help us eliminate the radical expression. So we can replace 1 plus tangent squared theta with secant squared theta by using this Pythagorean identity. And when we do that, we will have nine tangent cubed theta over the square root of secant squared theta times secant squared theta d theta. And of course in the denominator you have the square root of secant squared theta, and the squaring and the square root will undo each other and you just have secant theta. And the next thing that you can do is you can cancel the common factor of secant theta that you have in the denominator with one factor of secant theta in the numerator. And that takes us to, and you can factor out the 9 from the integrand, and that would leave us with tangent cubed theta times secant theta d theta. And again, what have we accomplished? Using our trigonometric substitution, we took our original problem and made it look like a problem from section 8.3 where we dealt with trigonometric integrals. So now we will remember some things that we learned in 8.3 to help us find our indefinite integral from this point forward. And remembering certain basic differentiation rules and their corresponding integration rules can help you decide how to proceed when you see something like what we have here. One thing that we can take advantage of is this Pythagorean identity, and how you should proceed is something that is an intuition that you will develop after doing a number of these problems. You'll have a better idea of how to proceed to go from what you have to finding an antiderivative. But in this particular problem, here's what we're going to do. We're going to begin by writing tangent cubed as tangent squared theta times tangent theta, and then we have secant theta d theta. And what would be the next thing that we might think about doing? We might think about doing a u-substitution, a regular u-substitution, if you want to call it a regular u-substitution rather than a trigonometric substitution. We can see that what we have here is secant tangent, although I have it written as tangent secant. But secant tangent is the derivative of secant. So if I let u be equal to secant x, or secant theta, then du will be equal to secant theta times tangent theta d theta. But how can I let u be equal to secant theta when what I have here is tangent squared theta? I can rewrite tangent squared theta by using this Pythagorean identity. So that will become tangent squared x is equal to secant squared x minus 1. And we're going to replace tangent squared theta with secant squared theta minus 1. So we have 9 times, and we're replacing tangent squared theta with secant squared theta minus 1. And we had tangent theta times secant theta, or you can write it in this order, d theta. And now we're going to do a regular u-substitution. Let u be equal to secant theta. Then the differential of u would be secant theta times tangent theta d theta. And this substitution would allow us to change variables to go from theta to u. I'd like to point out that we began with the trig substitution and we changed variables from x to theta. And now we're going to proceed to find an antiderivative for our indefinite integral by using a regular substitution, a regular u-substitution. And using that, we will now change variables from theta to u. Then we will find an antiderivative in terms of u. Use this substitution to go back to an antiderivative in terms of theta, and use our trig substitution to go back to an antiderivative in terms of x. So now we have 9 times, I will replace secant theta with u, so we have u squared minus 1, and secant theta times tangent theta d theta will be replaced with du. And of course, this is something that is very easy to integrate. You would use the power rule for integration, add 1 to the exponent, and divide by the new exponent. And this is what we have as our antiderivative in terms of u. It is a straightforward matter to go back to an antiderivative in terms of theta. Just use our u substitution here. So we're going to replace u with secant cubed theta over 3, or 1/3 times secant cubed theta, minus u, minus secant theta, plus c. So the next thing that you can do is go back to x. And the way you go back to x is by referencing your trigonometric substitution from the beginning of the problem. So our trig substitution was x is equal to tangent theta. So tangent theta is equal to x over 1. And you should draw a right triangle label an acute angle theta, and we know that tangent is opposite over adjacent. And we can find the length of the hypotenuse by using the Pythagorean theorem. So C is equal to the square root of 1 plus x squared. With that, we're able to go back to our original variable of integration, which is, of course, x. So what we need to do now is we need to go back to x by using what we know about secant. Secant is the reciprocal of cosine. So secant of theta would be hypotenuse over adjacent. So here's our angle theta. This is the hypotenuse, and this would be the length of the adjacent side. So now we're able to write 9 times 1/3 times secant of theta is the square root of 1 plus x squared. And then we're going to go ahead and cube that, minus secant of theta, which is the square root of 1 plus x squared, plus our constant of integration. You can distribute the 9 to each of the two terms if you would like to, and if you choose to do that, 9 times 1/3 is 3. And of course you can write the radical expression raised to the third power in different ways. One of the ways you could do that is write that as 1 plus x squared to the 1/2 for the square root, and raise that to the third power, power of a power, multiply the exponents, and you could write that as 3 over 2 for the exponent, minus 9 times the square root of 1 plus x squared, or 1 plus x squared to the 1/2, plus c. We are done with the problem because we have expressed our antiderivative in terms of our original variable of integration x. Today we looked at a couple of examples for trigonometric substitutions, and you look at the form of the radical expression in the integrand to decide which of these you should use. And then once you've decided, you proceed with the steps where you use your trigonometric substitution to change variables, and then you're going to eliminate the radical expression by using a Pythagorean identity to rewrite the radicand, and then you will integrate to find an antiderivative in terms of theta, and then you will go back to your original variable of integration by referring to your trig substitution and drawing a right triangle. One thing that we did see from our examples today is that the answers could be expressed in different but equivalent forms. The antiderivatives could be expressed in different but equivalent forms.